Welcome to this tutorial on multidimensional arrays and large data management in MATLAB. As many multidimensional datasets grow in size, for example due to increase in model resolution and remote sensing capabilities, we are becoming increasingly limited in our ability to handle large datasets. In this tutorial, you are going to learn practically how to handle large datasets using the concept of multidimensional arrays in MATLAB. So, what are you to expect from this tutorial? You're going to learn about the concept of multidimensional arrays, what are multidimensional arrays and the examples, how to organize data in multidimensional arrays, when do we need to use multidimensional arrays? We'll learn how to work with multidimensional arrays. And finally, we have a lab section on practical examples and applications of multidimensional arrays in MATLAB. What are multidimensional arrays? Often we need to subset a large global grid to look at data for specific points, particular region, or select a specific time slice. Then we may want to apply statistical functions to these subset groups to generate summary information and carry out other analysis. Hence, we require tools that are optimized to handle large datasets that have many variables spanning in dimensions of time and space. What are multidimensional arrays? As we've seen in previous tutorials, a vector is a one-dimensional array and a matrix is a two-dimensional array. A multidimensional array is an array with more than two dimensions. Multidimensional arrays in MATLAB are extension of the normal two-dimensional matrix. In matrix, the two dimensions are represented by rows and columns. Now, since multidimensional arrays are extension of two-dimensional matrices, the multidimensional arrays use additional subscript for indexing in the various dimensions. So, a 3D array, for example, uses three subsets. The first two are just like a matrix, where you have your rows and columns. But the third dimension represents pages or sheets of elements. Also, you could have a fourth dimension which can represent a collection of books. How do we organize data in multidimensional arrays? You can use multidimensional arrays to represent data in two ways. The first way is as collection of two-dimensional data, where you treat these pages as matrices. The second way is to look at it as multivariate or multidimensional data. For example, you might have a four-dimensional array where each element corresponds to either a temperature or air pressure measurement taken at one of a set of equally spaced points in a room. For example, consider an RGB image. For a single image, a multidimensional array is probably the easiest way to store and access such data. If your data come in multiple dimensions, for example, climate data in space and time, where you have X, Y, Z, and time, 4 dimensions, or images that come in multidimensional datasets, such as RGB values, red, green, and blue values, or remote sensing images that come in several bands, such as the Landsat 8 images. If your data are structured on a regular grid, you can also apply the concept of multidimensional array. And thirdly, if you can represent your data in any of the geoscientific data formats, such as CDF, NetCDF, or HDF format, then you can apply the concept of multidimensional array. So in general, if your data come in multiple dimensions, for example, climate data in space and time, then you can apply the concept of multidimensional arrays. So if you have different variables such as temperature, precipitation measured at latitude and longitude grid points and collected over a reference time, then multidimensional arrays can be applied to such datasets. It's also possible to apply multidimensional arrays where you have just one variable, such as air temperature, measured at different grids over different time period. Another example is space weather data that come in space and time. These datasets are measured at specific latitude, longitude over different altitude or elevation in different time interval. You can also apply multidimensional arrays to images. Usually images come in different color values. For example, the red, green, and blue images can be represented as multidimensional arrays. So how do we create multidimensional arrays? Usually there are two ways you can create a multidimensional array. First is by creating a two-dimensional matrix and then extending it into further dimensions. Secondly, you can use the cat function, the concatenate function, to build multidimensional arrays. This function concatenates a list of arrays along a specified dimension. The syntax for the cat function is simple. Simply define a new array, use the cat function, specify the dimension, and include the matrices you want to concatenate. N is the new array created. M1 to Mn are the arrays to be concatenated, that is combined, while dim is the dimension along which to concatenate the arrays. Practical application of the cat function is band combinations of satellite imageries to extract unique and new information. For example, if you look at the Landsat 8 band combination, for natural color you combine band 432. For agriculture, for example, you combine band 652. So using the cat function in MATLAB, you are able to combine these different bands of imagery in order to carry out different analysis and extract different information. Here's an example. We read bands 1 to 7 of Landsat 8 image using the image read function in MATLAB from band 1 to band 7. And then we use the cat function to create various combinations. For example, if we want the natural color combination, we concatenate in the third dimension, band 4, band 3, band 2. To carry out analysis on land and water, we concatenate band 5, 6, and 4. While to carry out vegetation analysis, we concatenate band 6, 5, and 4. And then we can view the composite image using the function imShow, meaning image show, with the image as input to the function. So how do we subset a multi-dimensional array? Subsetting such an array involves reading everything into in-memory array, and then you cleverly use matrix algebra to look for a specific range of index values associated with the temporal or spatial slice needed, and also for summarizing data across spatial and temporal dimensions. A portion of an n-dimensional array can be extracted by specifying the range of index in each dimension. For example, to get a subset of an n-dimensional array, we simply define the array and define the subset in each dimension. So A1 to A2 represent the range in the first dimension, B1 to B2 represent the range in the second dimension, continuously. It should be noted that elements of multidimensional arrays can be moved around in many ways, similar to vectors and matrices. Reshape, permute, and the squeeze functions are useful functions for rearranging elements in a multidimensional array. Note that for numeric arrays, all rows must have the same number of elements. Similarly, all pages must have the same number of rows and columns. Let's look at some of the functions used with multidimensional array. The reshape function operates column-wise by creating a new matrix taking consecutive elements down each column of the array, starting with the first page, then moving to subsequent pages. You can change array shape by respecifying the array's rows, column, or page dimensions while retaining the same number of elements. The syntax for the reshape function is simple. We define a new array B, and then we'll call the reshape function with the array we want to reshape and the size of the new array. S1, S2, S3 is a vector specifying the new size. We'll see more of this in the lab section. The permute function reorders the dimension of an array. For example, it's possible to have an RGB image rearranged as GRB, BGR, and so on. This will create different combinations of the image. Likewise, a band combination of an image can be rearranged for the purpose of analysis to be carried out. To use the permute function, simply call the permute function, define the array to be permuted, and specify the new dimension. Dimension is a vector specifying the new order for the dimensions of A, where 1 corresponds to the first dimension, which is the row, 2 corresponds to the second dimension, the columns, 3 corresponds to pages, and so on. The next function to consider is the squeeze function, which removes singleton dimensions from an array. For example, given the array B with size 2, 3, 1, 4 in the first, second, third, and fourth dimensions respectively, we call the squeeze function and look at the size of the new array created. You see the singleton dimension has been removed. Thus, by squeezing B, we remove the singleton dimension and we have 2, 3, 4 as the new size of the array created. Other common functions used for multidimensional arrays include the ndim, which gives the number of dimensions in array A. We have the num_el, which gives the number of elements in the array A. We also have the flip function, which flips an array along the specified dimension. The min function returns the mean of an array along a specified dimension. Now, it's possible to have missing values that have been represented by nan, N-A-N. So to compute the mean or other statistics, you always will want to add the word nan and then the function name. So nan_mean will compute the mean of A, excluding missing values that have been represented by nan. Let's consider some practical examples and applications of multidimensional arrays in MATLAB. Feel free to play, pause, stop, and rewind the video. Practice each section before moving to the next. See you in the lab section. Thank you. Welcome to the lab section on multidimensional arrays and large data management in MATLAB. In this lab section, we are going to be making use of an M file, which is simply a MATLAB file saved as .m. The file contains comments and the codes we are going to use for this tutorial. This is to keep the time period for this tutorial as short as possible. So based on the lessons we've had in the theoretical section, first we are going to start with creating multidimensional array in MATLAB. So here is the M file. The first part is creating multidimensional array. You can create a multidimensional array by creating a two-dimensional matrix first and then extending it. For example, if we define a 3 by 3 matrix as the first page in a 3-dimensional array by creating a matrix P, we simply select the line of code or right click, and we either hit the F9 button or we simply click on evaluate selection. So this has created a 3 by 3 matrix P. Hence, P is a 2-dimensional array with D1, D2 as the row and column. Now we can add a second page, that is a second dimension. To do this, we can assign another 3 by 3 matrix to the index value 2 in the third dimension. The syntax P column 2 uses a column in the first and second dimensions to include all rows and all columns from the right hand side of the assignment. Thus, we can assign the second page of P another 3 by 3 matrix. So let's run this. Let's see the size of P presently. You can see that the size of P has changed to a 3 by 3 by 2. So we have two 3 by 3 matrices giving us 3 dimensions: the row, the column, and the pages. We can also create multidimensional arrays using the cat function. The cat function can be useful for building multidimensional arrays in a process called concatenation, that is, linking together in a series. For example, we can create a 3-dimensional array Q by concatenating P with a third page. The first argument indicates which dimension to concatenate along. So we can concatenate M and P and assign to a new array, or we simply update the pages of the existing array P. To do this, we use the function cat, specify the dimension which we want to concatenate along. We include the base array and the new array M to be added. So let's create the array M. So we have M as 3 by 3. We can simply create a new array Q and then concatenate P and M together. You can simply hit the F9 button on your keyboard. So we can see Q is a 3 by 3 by 3 array. Since P is of 2 pages and M has been added to P, we now have Q being a 3 by 3 by 3 array. We could as well enlarge P directly by adding M to the pages of P. P concatenates along the third dimension of P, and then we simply add the new matrix M to P. So we could see similar result is obtained for P and Q. So you can either concatenate into a new array, or you simply update an existing array by adding more pages to it. Alright, let's see some practical examples of using the cat function. Here we are going to load 3 matrices saved in text files. So we have the text files named as b.txt, g.txt, and r.txt. Let's view the contents of one of these files. We can see the contents of the files as simply integer values. Since the contents of the files are integers, we simply load them as integers using this function. So let's run for B, G, and R and load the text files to our workspace. Alright, now we have B, G, and R matrices loaded in our workspace, B, G, and R. You may want to view the contents of one of them. Okay, so we'll see them as integer values. Now we have three different matrices, each of 2 dimensions and of the same size, B, G, and R. We can therefore concatenate them into a single multidimensional array as follows. So we call a variable parrot and we concatenate in the 3rd dimension. Since each of them are 2-dimensional matrices, we concatenate in the 3rd dimension R, G, and B. So let's run this. Let's view the size of the variable parrot. We can see the size, the row, the column, and the pages. The next thing we want to do is we want to view the individual arrays R, B, and G using subplot. Here we define a subplot consisting of 1 row and 3 columns, and then we specify the first subplot here, the second subplot, and the 3rd subplot. In the first subplot, we use the function imShow R. This is image show to display an image. So for subplots 1 to 3, we want to display the matrices R, G, and B as images. We can simply run these lines of code. Here we have our 3 matrices R, G, and B. So we can see that those integer values were actually values representing an image of a parrot. Next, we want to see the multidimensional array of the parrot, which we have concatenated here in line 42. So we have created a multidimensional array by combining the R, G, and B value, red, green, and blue values together. So let's view what we have for the concatenated variable called parrot. We can add a title to it. Wow, this is nice. Now, we notice that the individual subplots holding R, G, and B gives us more like black and white images depending on the integer value of each pixel. The concatenated image combines the red, blue, and green values together to give us a complete color image of the parrot. So this is another example of what we can do with the cat function, where we can combine different matrices together and then form a composite matrix or multidimensional array. The next thing is we want to see another example of how we can combine bands of satellite imagery using the cat function. So in this example, we are going to be making use of Landsat 8 images. So we can navigate to the Landsat folder consisting of the various images. So the first thing is to read the bands 1 to 7 of the Landsat 8 images. The bands are saved already in this folder, as we can see the names. So line 65 to line 71 enables us to read using the image read. We read the 7 bands of the images into our workspace. Okay, now we have bands 1, 2, 3, 4, 5, 6, 7 in our workspace, and if you look at this, you will see they are all of the same sizes from B1 to B7. We can go ahead and use the cat function to create various band combinations. For example, if you want to carry out analysis based on natural color, this is defined as we saw in the theory section by combining band 4, band 3, and band 2. So we simply define the variable which we have called natural color, And then we use a cut function. We specify the third dimension because each of this band is a two-dimensional matrix. So we are combining in the third dimension, band 4, band 3, band 2. For analysis related to land water, we combine band 5, band 6, band 4. And then for vegetation analysis, you combine or concatenate band 6, band 5, band 4. So by running this, you will create a multi-dimensional array consisting of this different band combination. So look at our workspace. We have the land, which is now a 3-dimensional array, the natural color consisting of 3 bands, and we have vegetation analysis consisting of 3 bands. So with this, you can create different combination of satellite images depending on the kind of analysis you want to carry out. Let's look at another example still on the cut function, where we can carry out various combination of RGB images. So let's see the effect. Here we read the image called parrot1.png. This is another image of a parrot. Okay, so we run this. Alright, parrot does not exist because we're in the Landsat folder. So let's go back to the lab folder and try running again. Okay, so we have the parrot image, and then of course from the dimension or the size, we could notice that this is a smaller image, 200 by 150 by 3 pages, representing the red, the blue, and the green values. Now that we have our red, green, and blue values, we can try to concatenate using the cut function to create different combination of the 3 colors. So for P1, we concatenate red, blue, and green. For P2, we concatenate red, green, and blue, and then up to P6, having different combination of the 3 colors. So let's run this. Okay, that's successful. The next thing we want to do is to display the 6 different combinations using subplot. So now that we have 6 different combinations, we define a subplot having 2 rows, 3 columns, giving us a total of 6 plots. And then for the first plot, we show the value of P1. And we add a title so that we know the combination for that particular image. So we run this from line 95 down to line 112. All right, now we have our 6 combination of our 3 colors RGB. So this gives us RBG. This is the original image, which is made up of R, G, and B. Image 3 is BGR. So we can see using the cut function, we can actually create different combination of our colors, and then we have different outputs. The next section is storing multiple datasets using the cut function. Here, the cut function allows you to combine multiple data into one multi-dimensional array. For this example, we are going to be making use of daily soil moisture data. The data for this example is in netcdf format. Do not worry if you are not familiar with this data format. In the subsequent lesson, you will learn about working with various geoscientific data formats such as the CDF, the netcdf, the HDF, and others. For now, let's focus on the example on how to use the cut function to combine multiple datasets. So let's read the latitude and longitude from one of the data files. Next, we define variable 001 to 005 representing the daily soil moisture data. So we'll simply read the 5 days soil moisture data. Alright, so this data is measured at grid points, latitude, longitude. So for each day, we have two-dimensional data. Hence, we can combine the daily data in the third dimension using the cat function. So to do that, here we are using soil moisture 2020 to represent the soil moisture for that particular year. And then we use the cat function, specify that we are combining in the third dimension, which is the daily value. And then we specify the daily variables which we have created, 001 for day 1, 002. So you can do this up to day 365 or 366 if it is a leap year. For this example, we're only concatenating for 3 days measurement. So we run this. Okay. Alright, we can see the size of what we have created. Okay, so we can see we have 1, 2, 3 dimensions. So this represents the latitude, longitude measurements, the soil moisture at this grid point, and the 5-year represents that we have combined or concatenated 5 days measurement. You can also combine further into higher dimensions. So for the purpose of this example, let's make a duplicate of the soil moisture variable and rename it as soil moisture 2021 so that we have 2 years data. Okay, so we'll create another variable, call it 2021, and we assign it the same value for 2020 such that we have 2 years data for the purpose of the example. Okay, so now we have soil moisture for 2021 and for 2020, each having 5 days observation and each of 3 dimensions, latitude, longitude, and days. So since each is in 3 dimensions, we can combine into a 4th dimension whereby we combine all the yearly observation. To do this, we simply use the cat function. We define another variable called soil moisture by year, and then we use a cat function. Here we specify the 4th dimension because each of these is already in 3 dimensions. So if we run this, and then we try to look at the size of the new array, you discover we have 4 dimensions, as we can see in the workspace, 4D. Okay, so the latitude, the longitude, the days, and then for each year. In this case, we have 2 years. Okay. Next, we want to look at accessing element of multidimensional arrays. Let's recall our matrix P. Okay, so we have our matrix P as a 3-dimensional matrix. So, to access element in a multidimensional array, we simply use integer subscript just as you would for vectors and matrices. For example, to find the 1 by 2 by 3 element of P, which refers to the element in the first row, second column, and the second page of P, we simply use, okay, we've defined a variable R1, C2, P2 just to represent row 1, column 2, page 2. and then we have it as 1, 2, 2. First row, second column, second page. So if we run this, we have the value of 11. So look at this. The first row of the second column of the second page. This is the second page of P. The first row is this. And then the second column is this 11. So the function P122 takes us from the second page, the second column of the first row. Likewise, we can use index vectors such as this 1, 2, 3 in the second dimension to access only the first and last columns of each page of P. So let's clear the screen. So let's try running that. Okay, so this gives us the first and last column of each page of P. The column operator here represents all the pages or all the pages in that particular dimension. So we have the first and the third column of each page, page 1, page 2, and page 3 of P. To find the second and third rows of each page, we use the column operator to create our index vector. So we simply divide the second and third row of each page. So we have the second to the third row of each page, all the column, all the pages. So this gives us the second and the third row for page 1, page 2, page 3. So for more examples, let's refer back to our soil moisture data example. Assuming we have the soil moisture data for just 5 years, we are going to be managing the following number of data points: the latitude number, number of longitude for 365 days and for 5 years. You have over 368 million data points. Okay, and this is just for 5-year data. Now, with the concept of multidimensional array, you can easily, efficiently, and effectively access every data point of interest in this over 368 million data points. So let's go back to our example. To access all the grid data for day 1 of the first year, all the grid data meaning all the latitude using our column operator, all the longitude, this is the third dimension represent the days, so this is for day 1. The fourth dimension represent the year, and this is for the first year. So this will give us access to all the grid data for day 1 of the first year. Okay, we have that. Yeah. If we were interested in day 4 soil moisture data for the second year, here we use day 4_21 to represent day 4 for 2021. Okay, so we have the column operator representing all the latitude, all the longitude, day 4 for the second year. So we can run this and we have that created. We can also subset data for day 1 for each year. Okay, day 1 for each year. In that case, we use column operator to represent all the latitude, all the longitude for day 1, and then the column operator to represent for all the year. Okay, so we'll run this and we can view the size. So we can see we have all the latitudes, all the longitude for day 1 for the 2 years data. So let's make an assumption here. If we have 2 years data called soil moisture value with size 256 by 806 for the latitude and longitude, and for the complete year, 365 days, for 2 years. Okay, we can subset the data for each month of the year as follows. For January data, we know that January is from 1 to 31. Okay, day 1 to day 31. So by using this function, the first dimension here represents all the latitude or the longitude for days 1 to 31, which is January, and for all the year. Okay. Similarly, if we want data for February, that will be all the latitude, all the longitude. February is 32 to 56, using day of the year from 1 to 365 or 366 for leap year. So we have all the latitude, all the longitude, day 32 to 59 for all the year. Now you have to be mindful of leap year because February will be 32 to 60 for leap year. Okay, so this is how you can actually subset a multi-dimensional array consisting of yearly data of daily observations. So since most of our scientific data sets come as global data covering the entire Earth, sometimes you are interested in getting a subset or a region of the globe based on the latitude and longitude ranges. Now, if we want to subset a regional data, we can define that by using the indices of the grid covered by the region. Assuming we are interested in the soil moisture covering plus or minus 10 degrees along the equator and plus or minus 10 degrees along the Greenwich. So let's look at our latitude. This is our latitude data. Okay, so we have from plus or minus 90 degrees north and south. So we can scroll down to see at what point we have plus 10 degrees and minus 10 degrees. Okay, so this is approximately 10 degrees. At the index of 91, we have 10 degrees approximately, and then we can scroll down to see where we have minus 10 degrees. Okay, this is at 162, which implies that the latitude range of minus 10 degrees to plus 10 degrees falls within 91 to 162 in latitude. So you can do the same for the longitude to see what range you have plus and minus 10 degrees. So here we have approximately 10 degrees around 335 minus 10 degrees. So we can continue moving to see where we have plus 10 degrees. For longitude range, from 335 to 390 defines plus or minus 10 degrees. So coming back to our code, since the latitude range is the first dimension and the longitude range is the second dimension, we can specify plus or minus 10 degrees in latitude by simply defining the indices for that range, which is from 91 to 162. While plus or minus 10 degrees in longitude, as we saw from the longitude variable, is from indices 335 to 390. So this will give us a subset of our global data covering plus or minus 10 degrees in latitude, plus or minus 10 degrees in longitude for all the days and for all the year. Okay, so we can simply run this. Let's see the size of the region we just subsetted. Okay, 72 by 56. So we have 72 latitude grid points, 56 longitude grid points for 5 days and for 2 years. Okay. Sometimes you may be interested in the data for an entire period just at a single grid. In that case, you define the grid. You have to know the indices for that grid. So here we are using the equator. Okay, so when you look at your latitude and longitude variable, and then you try to scroll down to look at where you have 0 for latitude and 0 for longitude, you have indices 126 for the latitude, 363 for the longitude of the 0, points in the data. So here we define the specific latitude and longitude for that grid of interest. We use the column operator to get the data for the entire day and then for the entire year. Okay, so let's look at the size of this new variable. Okay, so you can see we have 1 by 1 because we are referring to just one grid point. 1 by 1 for 5 days and for 2 years. So with multi-dimensional array, we are able to handle large data sets regardless of the number of observations. It could be a global data covering the entire globe, measured daily for 365 days or 366 days, and for a period of 20 years. All of these can be concatenated or stored as a single multi-dimensional array for easy access and manipulation. So next, let's see how do we manipulate multi-dimensional arrays. Since we are now familiar with creating and accessing arrays, let's load some sample data for this section of the lab section. So for this example, we simply load a sample multi-dimensional array data. Okay, our data is loaded. The data is actually a gridded monthly mean total electron content for a period of 19 years, from 1999 to 2017, all stored in one multi-dimensional array variable. This once again demonstrates the advantage of working with multi-dimensional dataset and how it can be used to handle very large datasets. So let's see the size of the data we just loaded. Okay, so here we see the latitude, the longitude. Since it is monthly data, we have for 12 months, January to December, and for 19 years. Okay, we can simply calculate how many data points have been stored for this variable, which is 33 times 16 times 12 times for 19 years. So we have 120,384 data points stored in this variable referred to as monthly tech, which is monthly total electron content value for a period of 19 years. So here we want to demonstrate how to reshape a multidimensional array. As we've seen in the theoretical section, the reshape function is basically used to change array shape, so we can combine all the monthly data for the 19 years period using the reshape function. We simply define a new variable. Okay, we call the reshape function. We define the variable to be reshaped, and we specify the new size. So here we are using 33 by 16 by 228. The 228 here means we are combining the 12 months data for 19 years. So that is how we have. So we've been able to combine all the monthly data for the 19 years period using the reshape function. Okay, so we have this. Okay, now we can look at the size. So we have 33, 16, 228. So it means we have 228 monthly data for that period of 19 years. We can find the monthly mean value over each grid for the 19 years period. Now, since the months are in the third dimension, we specify the mean to be the mean of the third dimension as follows. So we'll define a variable called monthly mean. We'll call the mean function, the variable whose mean we want to compute, and the dimension, in this case the third dimension. So we can run this. Okay, and we have our monthly mean. You can look at it, 33 by 16, because it is the mean for the entire 19 years period. We can view this using a custom plot function that has been created, and then give it a title. Okay, so we can see the mean value for the entire 19 years monthly mean. Okay, so this gives us the value for the 19 years period. Another key functions with multidimensional arrays is permuting array. Okay, so the permute function allows you to reorder the dimension of an array. Okay, sometimes your data could be in latitude longitude format, but your analysis is in longitude latitude format. So you want to swap, you want to permute, change the order from latitude longitude to longitude latitude. Okay, so let's recall our monthly take. Okay, so we have it as 3 by 16 by 12 by 19. Okay, we can decide to swap, that is permute, between the month and the year. So to do this, we define a new variable for the purpose of the example. We'll call the permute function, the variable that we want to permute, and then the new dimension. So here you can see we have changed the order to be 1, 2, 4, 3, meaning latitude, longitude, year, and months. So if we run this and view the size, you can see we now have latitude, longitude for 19 years for 12 months. So with the permute function, we've been able to swap the order between the year and the month. Okay, this is also important when you want to reorder your data from latitude, longitude to longitude, latitude. So we can swap our latitude and longitude using the permute function. Take note that here we have 33 for latitude, 16 for longitude. So we do this, and then we can look for the new size. So now we have 16 by 33. We've been able to swap from latitude, longitude to longitude, latitude. So that is another application of the permute function. In the last part of this tutorial, we want to look at carrying out computations with multidimensional arrays. Now it should be noted that many of the MATLAB computational mathematical functions accept multidimensional arrays as argument. Hence, these functions operate on specific dimensions of multidimensional arrays. That is, they operate on individual elements, vectors, or matrices. So once you are able to carry out a subset of your multidimensional array, you can carry out all mathematical computations and arithmetic computations as well. We have seen some examples earlier, such as calculating the mean in a specific dimension. Now, when you are using missing values in your data, which may be represented by NaN, it is advisable you use the MATLAB functions that ignore the missing values if you intend to ignore them. Okay. Example include NaN max. So this will compute the maximum value ignoring the missing values, which have been represented by NaN. NaN mean we compute the minimum value ignoring missing value, and then NaN mean we compute the mean ignoring missing value. Let's have an example for this. First, we create a matrix M and intentionally add some NaN values for the purpose of our example. So we have our matrix M. Okay, so this is the matrix M. Let's introduce some NaN values. So we have none here, some nones here, none, and then in the fourth column we have no none. Okay, now if we find the mean of m using the conventional mean, all the columns having at least one none value will return a mean of none. That is, if we do this, the mean, just using the mean, so you can see all the columns having at least one missing value will return a none as their value, while the fourth column that has complete data will return the actual mean. But sometimes we want to compute the mean ignoring the missing values in our data. In that case, we simply use the none mean and then the matrix we want, or the array, multidimensional array, we want to compute its mean. So with the none mean, it computes the mean ignoring the missing value. Let's clear the screen and repeat this. Our m and then our none mean. So we can see this gives the mean of this. Here we have just 2, so the mean is 2. The mean here is computed, and the mean of the fourth column is as well computed. So with the none mean, you are able to compute your mean ignoring missing values. So for every operation or computations in MATLAB you want to carry out, which includes missing values that have been represented by none, N-A-N, you simply use MATLAB functions that have the none before the name of the functions. Examples have been given here: none max, none min, and none mean. So we've come to the end of this lab section. This brings us to the end of this lab section. The M file we have used for this tutorial will be provided as a link so you can download and then practice with your own datasets. In our subsequent lesson, we are going to learn about working with various scientific data formats used in geosciences. Since most of them come in multidimensional arrays, it will be a good follow-up lesson. Stay tuned for that lesson. Don't forget to subscribe for free, like the video, share, and turn on notification to receive future lessons. Thank you and see you in the next lesson.